Let's talk quickly about transistors and how we can use them to build logic gates. So first let's look at this abstraction layer cake here. Transistors are built using concepts from physics and chemistry, and we get the transistors. Now transistors are basically variable switches, and so we have a kind of a history of these types of variable switches. Back in the 30s we had relay logic, in which you had a coil that was an electromagnet that was used as an input to that coil, would open or close a switch, a mechanical switch. Then we had vacuum tubes, such as your old CRT monitors, CRT TVs, and those worked in a similar concept. They had an input that would vary the amount of current flow between two contacts within the vacuum tube. And in other countries they also call these vacuum tubes valves, and you can think of them very much as like a water valve. You can give an input to a particular segment of this and it will control the flow of electrons. And then we ended up with transistors, and there's many different types of transistors out there, and we're just going to focus on the main concepts of transistors in general. So we're going to look at two different types of transistors right now. One is called NMOS and one is called PMOS. A transistor has three inputs. You have your source, your drain, and your gate. And if we equate this, for instance in this NMOS transistor right here, if we equate, if we equate the source and drain to the different ends of this switch, what we're trying to get to happen is an input from the gate will either allow or disallow current to flow from the source to the drain. And so depending on the chemistry, you can have different inputs to cause this to happen. So with an NMOS transistor, if I want to basically replicate the functions of an open switch where no current can flow, then I want to put a 0 on my gate input, and that's going to make it so that current cannot flow from source to gate. Now if I want it to flow, if I want all the current to go from my source to my drain, then I put a 1 on my gate, and that basically just turns on the transistor, and then current can flow from source to drain. The other kind of transistor we're going to talk about is called PMOS, and it works in the inverse way. And I have this little bubble on my input here. Anytime you see a bubble dealing with transistors or digital logic, that means invert. So what I'm going to have is, if I want to replicate the functionality of no current flowing between the source and the drain, so no current, then I have to put a 1 on my gate. So I can fill that out here. Well, let me delete those and then fill that out here. And if I do want current to flow from source to drain, I simply put a 0 on my gate. And that's all I need. So now I'm going to use these, and we're going to cleverly arrange them such that we get functions that can allow us to do Boolean operations. And so the first gate that we're going to look at is the simplest. It is called the inverter or the NOT gate. And the inverter basically just inverts whatever the input is. It's got one input here and one output there. So this is, we're always going to have our inputs on the left and our outputs on the right. And so we have X comes in, whatever it is gets inverted. So let's see what happens here. So if I give a 0 for my X, let's see which signal, either the 0 or the 1, is allowed to flow to the output. And so we're not talking literal current flow at this point, I'm talking signal flow. So which one of these switches gets turned on or which one of these transistors rather, gets turned on and which does not get turned on to allow current flow. So let's look at the NMOS down here. If I give a 0 here, then that means no current can flow through the NMOS transistor. So the 0 will not get forwarded to the output. However, if I look at the PMOS transistor, if I give a 0, then that does allow the 1 to flow to the output. So if my X is a 0 input, my F is a 1. Let's see what happens the other way around. What if I put a 1 on my input? Well, a 1 allows current to flow in an NMOS transistor, and it does not allow current to flow in a PMOS. So in this case, the signal flow is that a 0 will get forwarded to the output. And so that's exactly what I have here. If there's a 0 on my X input, there's a 1 on my output. If there's a 1 on my input, there's a 0 on my output. And this might not seem very useful. However, this does what's called the ones complement. And this is part of the twos complement, which, if you remember from class, the twos complement is how we find the negative of a particular binary number. And so the first step in that is to find the ones complement, which we can easily do using inverters. Let's look at the next gate. This is called an OR gate. And the way an OR gate works, again, is a clever arrangement of our NMOS and PMOS transistors such that we get a function that will do what we typically think of as a Boolean OR operation. And that is, and you can kind of simulate it here with these switches, this relay logic here, if either X or Y are closed, then the signal on our input here can get passed to the output. So if I want to close the Y, then the signal can flow. If I want to close the X, the signal can flow. If I close both of them, the signal can flow. But if neither of them are open, the signal does not flow. So let's see how this works with the arrangement of transistors. So let's first give X a 0. So I've got my X's on this side and Y's on this side, just to simplify it. Our output is actually right here. This is our F. Let me actually do that with the gray so I won't overwrite it here in a second. So this is our output. And so let's see what happens if we get a 0 from our X and a 0 for our Y. What is our output of F? So if you'd remember, we're going to use the signal flow concept here again. So these are NMOS transistors on top, and both of them are 0. So there's no current flow or no signal flow through those transistors. Because NMOS, if we go back to the NMOS, if you have a 0 input, then you get an open switch. And let's go back and look at the bottom here, PMOS. Well, PMOS is just the opposite. If I get a 0 input, it does allow signal flow. So if I have got a 0 here for my ground, that signal can flow through Y because it's got a 0 input on the gate. It can flow through X and gets forwarded to the output. And so in this case, when X is 0 and Y is 0, or both of the switches are open, F gets a 0. And that makes sense if you look at this schematic here. So let me clean this up a bit. Oop, I want to keep that. So I had a 0 for my first row there. And I'm just going to erase these guys. And so the next concept is if X is a 0, but Y is a 1. So what happens if that's the case? So if I get a 1 on my Y and a 1 on my Y. Well, let's look at the NMOS case. In the NMOS case, I have a X over here with a 0, which does not allow current flow, and I have a Y, which does allow current flow. So I will get current flowing through this. Now let's look at the PMOS transistors. In order to turn off the output, there's no current flow here, then I need a 1 because of this inverting input. So if I give a 1 here, then current cannot flow through that one. And because these are in series, the X and Y, it doesn't matter what this is, because no current's going to get to that point anyway. It's going to stop before it gets there. So what we end up with is our output is a 1, because the only current flow that's possible is this 1 through the Y's NMOS transistor. So in our truth table, we can write a 1. And again, I'm going to erase this before I do that, just so I can clean it up a little bit. There we go. And that's the same as if I had my Y closed and current can flow. So now, let's take a look at when X is a 1 and Y is a 0. So if X is 1, Y is 0, what happens? Well, if Y is a 0 over here, in an NMOS case, no current flows. If I look at X, that does allow current flow. But let's look at the PMOS. With a 1 on the input, that says that yes, current can flow here. However, there is no signal to flow because Y is turned off, so it doesn't get forwarded. So our output is a 1 because the output comes directly through the X NMOS transistor. And so that says that if X is closed, then current can flow to the output. So let's go back and put that in our truth table. Now what happens if both Y is a 1 and X is a 1? Well, current can flow this way and it can flow this way. So a 1 comes out this direction. And since both of these are 1s and they're PMOS, they both are turned off. So the output here is a 1. And there we go. We've just built a truth table that shows our inputs and how they affect the outputs for an OR gate. And this is the symbol for an OR gate. It's kind of a bent back pointed tip. So let's look at another option here. This is called an AND gate. And I didn't label the outputs here, but the output F is right here. So let's try to see what happens when we're building an AND gate. An AND gate only allows current to flow if both of the switches are closed. So that means if X is a 1 and Y is a 0, no current flows. If Y is a 1 and X is 0, no current flows. But you have to have both of these switches closed in order for current to flow. So X and Y must flow. And so to get that functionality, we simply change our layout of transistors here. So now, if I have X is 0, Y is 0, we're going to look and see what our output might be. So with NMOS, X is 0, no current flows through either of those. But with these PMOSs, the current can flow, or the signal can flow, and therefore our output here will be a 0 because it connects to 0 straight through. So let me add that to our truth table here. Now let's see what we have if we have X is 0 and Y is a 1. Well, if we look in our NMOS case, there's no current flow through that transistor here for X, so it doesn't actually even reach Y, so that doesn't matter. And then in our bottom case, for X, this transistor is turned on, allowing signal flow. And the Y is a 1, so that's turned off. So the output here is a 0. So we can add that to our table. And what that basically says is, I put that in the wrong place. That was X is a 1. So that just says X is closed. Well, if Y is open, because it's a 0, then no current will flow. Similarly, if we look at if Y is a 0, if Y is a 1 and X is a 0, we have a similar thing happen. Because X is a 0 here, there's no current flow. So it doesn't matter what Y is. I've already done that one. Sorry. Let's try this again. Should be when Y is a 1 and X is a 0. What? No, that's what I just did. Okay, so what happens here? This transistor is turned off, so no signal can come this direction. And this transistor is turned off, so we get a 0 coming through our Y PMOS transistor. That gives us a 0. So that's this case here, row number 2 here. Sorry for the confusion there. Confused myself for a bit. And so now let's look at when Y and X are both equal to 1. Well, if this is a 1 for NMOS, current does flow here, and it flows through our Y. And since these are PMOS, if there's a 1 here, then no current can flow. So our output is 1. And so this gives us our Boolean AND operation. If X is a 1, X is closed, and Y is closed, then current can flow, and that's exactly what we have here. So that's the basics. Hopefully I didn't confuse you too much. And of course we'll talk about more concepts later. And in fact, this isn't technically how we build ANDs and OR gates. It's just, this is a good way to visualize the concepts. I'll explain in detail how we actually build these later on in the class, but for now, think of them in these terms, just in this setup. I won't ask you to draw the transistors typically inside of a gate, because the whole concept of engineering is to simplify and abstract things so we can do really hard things relatively easily. And so by using the logic gates, we'll instead use these symbols. So this is the AND gate. It's got a flat back and a bullet-shaped tip with X and Y on our inputs and F on the output. We've got our OR gate here. Again, it's a kind of a bent back and pointy tip. And then we have our NOT gate. And it is a triangle with, let me see if I can draw a straighter triangle here, with a bubble on the end, and it only has one input. So this is our schematic symbol for the NOT gate or the inverter.